Thanks. Okay, so last time I was trying to motivate why we might be interested in connecting the complex differential geometry of vector bundles and the complex algebraic geometry. Roughly speaking, the last thing that I said was this theorem, this famous theorem of Donaldson, Uhlenbeck, and Yau, that says if we fix a holomorphic vector bundle over a compact Kähler manifold, then we can find a Hermite-Einstein metric, giving us a canonical choice of Hermitian metric, if and only if the bundle satisfies this algebra geometric stability condition called slope stability. So what I want to do today is to explain why this sort of result could be true, and also then to use that motivation to produce more general PDs, where we're going to try and prove something like this in a certain large volume regime for these Z-critical connections, which is sort of what I'm leading to. So the first topic today is why should something like this be true? So why should something like the Hitchin-Kobayashi correspondence, namely the equivalence between some kind of geometric PDE condition and algebra geometric condition, why should this actually be true? So it follows a very general framework in complex geometry. So it follows what's known as the ideas behind the Kempf-Ness theorem. So it follows what I'll call the philosophy of the Kempf-Ness theorem, which connects these two different parts here, moment maps and geometric invariant theory. Essentially, the Kempf-Ness theorem is a theorem equating two different types of quotients. It's the quotient theory in Kähler geometry and the quotient theory in algebraic geometry. So we're going to consider first the algebra geometric side of the story. So I'll let G reductive act on XL, where X is projective. You can add smooth if you like. Maybe I'll add smooth. It doesn't really matter. And L is ample. And G being reductive means it's the complexification of a maximal compact subgroup. So this is equal to complexification of K, where K sitting inside G is maximal compact. As yesterday, if you're not so happy with reductive groups, you could imagine that G is GL and K is the unitary group, for example, or the other important case is when G is a torus, complex torus, C star to the R, and then K is just S1 to the R. Okay. So in particular, I'm going to fix omega in C1 of L, Kähler. And while we can't ask for a Kähler metric to be invariant under a non-compact group, we can ask for it to be invariant under a compact group. And so we ask that this is K invariant. Okay. So we would like a quotient motivated essentially by trying to construct moduli spaces. What we would like to do is construct a quotient of X by G. So we'd like a quotient of XL by G. So we can do this in two different ways, and essentially the connection between these two ways is the Kempf-Ness theorem. We can do this via algebraic geometry or complex geometry / symplectic geometry. We're doing complex geometry really here. So I'll phrase it like that. And so I'll first of all start off with the algebraic geometry. And both of these, essentially the point is that not all G orbits are actually parameterized by the quotient. When we take a quotient, we throw away certain bad orbits. The way we measure what bad means or what good means for orbits is not by using the full group from the perspective I'll take, but rather through one parameter subgroups of the group. So for rho, a C star sitting inside G, it's going to be a numerical criterion, much like slope stability. So we're going to associate a number to a point in X. So we take X and X. Then what happens, we can specialize X under the C star action. So the limit as t goes to 0 of rho of t dot x So X, capital X, the variety is projective, hence proper, so this limit exists. This is some x0, which is a fixed point of the C star action. So in particular, C star acts on the line above it. So when I say that G acts on XL, what I mean is there is an action of G on L that is compatible with the action on X. So in particular, I get a C star action over this line X0. On the other hand, this is a complex line bundle, holomorphic line bundle. So this is just a copy of C. And so we know what C star actions look like on C. They just send Z to T to the lambda Z for some integer lambda. That's just a classification of C star actions on C. So we've got a number, and in particular, I said this was a numerical criterion, and this is the number we'll use. So we'll set mu of, or actually, let me use nu instead. Nu of X rho, so this is a number we've associated to the point X and the one parameter subgroup rho. And I'll use the convention that this is minus this integer lambda. Okay. So this allows us to define the classes of points that we'll include in our quotient. So X is first of all, semi-stable if for all one parameter subgroups of G, this weight is greater than or equal to 0. If you change lambda to minus lambda, this would be negative, which would be the more original conventions. Stable if for all rho non-trivial, not just identically the identity. We actually have strict positivity of the weights. So this nu, this is the weight. So it turns out that stable actually implies that the automorphism group is finite. It's kind of easy to see that you cannot have C star actions in the stabilizer of X at least, but it also kills the unipotent part. So polystable is the version of stable that allows automorphisms, continuous automorphisms. So polystable if for all rho C star sitting inside G, if nu of X rho is equal to 0, so if the C star has weight 0, then actually the C star action preserves X. So C star lives inside the stabilizer of X under the G action. So this is the stabilizer. So if it induces automorphisms of X. Okay. So the point of these notions, beyond the connection that these are kind of numerical conditions, much like slope stability, the point in the quotient theory is the following result due to Mumford. One could be much more precise than what I'm about to say. Oh, question? Yeah. Oh, I do. Yeah, absolutely. Did I write? Yeah. Sure. Thank you. Yeah. I don't see any more typos. So. Oh, yeah, sure. Yeah, this is not. The right way of forming that sentence. If you, yeah, so I just want that it's semi-stable, and the only one parameter subgroups that have weight 0 are ones lying in the stabilizer. That's all I want. Which is, if you perturb the parts of the sentence, it makes a little bit more sense. But I think it's at least mathematically correct. Okay, so the point, the application to the quotient theory of algebraic geometry is there is a quotient X mod G that depends on this line bundle L. So what are the points of the quotient? They're not all orbits. Note that the semi-stability, stability, polystability, they're actually conditions on the orbit, one can see. But only parameterizing polystable orbits. Okay, so the polystability, the word we've been hearing a lot, really enters because they're the right things to classify in the quotient space. The other part that I'll need is that there is morphism In general, you just get a rational map from X to the quotient, but we get a morphism from the semi-stable locus. One proves that semi-stability is actually a Zariski open property, and so this is actually a variety. We get a morphism down to the quotient. So semi-stable is exactly the locus where we actually get a morphism down to the quotient. In fact, it's not so hard to produce this quotient. The content is showing that the quotient, as I'll momentarily tell you how it looks like, actually agrees with the one characterized by this. So in fact, using the language of algebraic geometry, what you do is you look at the section ring of our ample line bundle L on X. So this is just global sections. G acts on L, so G acts on global sections. I can look at the invariance. It's a theorem by reductivity that this is actually finitely generated, and I can take proj. So depending on how comfortable you are with the language of algebraic geometry, it's actually kind of trivial once you're happy with it to write down what the quotient is. But from this perspective, you don't really see so much about the geometry of the quotient. And the point of this result is that it geometrizes what the quotient actually does. Okay. So really, the point I'm trying to make is the connection between the quotient theory of algebraic geometry and of complex geometry rather than focusing on either of them individually. So I'm going to turn immediately to the quotient theory of complex or Kähler geometry. Okay. Yeah, any questions on this algebra geometric side? The point is that you're trying to form quotients, and these numerical conditions like stability are actually the things that enter. Okay. Now we kind of forget about the reductive group G, and we just focus on the fact that we have X, which is a Kähler metric, and a K action, and we try to take a quotient using that information. So we need extra information, which is a moment map. So a moment map, or now what we need is our K action on X omega, and actually the definition makes sense even if omega is only symplectic. We don't really need Kähler. So a moment map for this is a K equivariant smooth map mu from X to joule of Lie algebra. So this is Lie algebra joule. Okay, so I have to tell you, first of all, what K equivariance mean. Means we have, by hypothesis, a K action on X. And in particular, K, the Lie group acts on its Lie algebra just by the adjoint action. And so it acts on the joule of Lie algebra by the co-adjoint action. Okay, so K equivariance makes sense. Such that for all elements of the Lie algebra, I can think of these things in two ways. First of all, they're just abstract elements of a Lie algebra. On the other hand, I have an action of this group K on my manifold, and so I can think of elements of the Lie algebra as inducing vector fields. So I'm going to just use the same notation for this element of the Lie algebra and the associated vector field. Then the moment map condition, it's an equality of one forms. I can get a one form in two different ways. So I take my element V. That's an element of the Lie algebra, so I pair it, and I'm going to get a function from X to R. I can take the differential of that function, and I'll get a one form. But using the vector field in the symplectic form, I can get a one form in another way, which is just by interior contraction. I'll fix the sign convention that there's a minus here. It's not terribly important. But interior contraction, so this is just, I insert V in the first variable. Okay. So the point is that, I mean, one should imagine X is, I don't know, four-dimensional as a smooth manifold, real dimensional. And I'm trying to take a quotient by S1, it's a compact group. Then if I try to do something more naive, then the quotient has absolutely no hope whatsoever of being a complex manifold because you should imagine it's three-dimensional. So we need some extra information to take a quotient that comes from this notion of a moment map. Okay. I'll give an example that fits into this framework. There's a canonical way of constructing moment maps once I fix a lift of the action to the line bundle as we have here. So we let H be a Hermitian metric on L So the curvature of such a thing, this is a two-form with values in end L, but end L is just smooth functions. So I can ask that this is equal to omega for omega Kähler. So omega is the Kähler metric we chose before. It's a relatively straightforward exercise in Kähler geometry that such a metric always exists. The point then is that we get a canonical moment map. In particular, such moment maps always exist in the setting that we're considering by the following formula. So for S, a trivializing section, so a nowhere vanishing holomorphic section, of our holomorphic line bundle near some point X. So what we do is we consider, so I need to give you a function after pairing with my element of the Lie algebra. And what I do is I take the log of the norm of the section, but I use my C star action to pull back the section, at least locally, near X. If I take the norm of this thing, this is a function. So I take the norm using this Hermitian metric, and then I can differentiate this. And I include my conventional sign. Okay, so the point of this formula is just that there's a canonical way of getting such a moment map. We don't really need to make any choices. We just get one for free. Okay. So we set X mod K mu, this quotient that I'm going to tell you more about, to be mu inverse of 0. Mu is a K equivariant map. 0 is a fixed point of the K action here. And so mu inverse of 0 has a K action as well. So I can take the quotient of mu inverse of 0 by K. At least this passes the dimension check that I mentioned before. So it seems plausible that this could admit the structure of a complex manifold or a Kähler manifold. Okay, so I'll now mention the main theorem that connects the geometry of this more kind of symplectic or topological quotient to the algebra geometric quotient. There are actually many names that have contributed what I'll say, in particular because I'm not going to worry so much about singularities, and so it really goes beyond the original work, which is due to Kempf-Ness and then Kirwan. But what I'll say is at least true. Okay, so first of all, my point X and X satisfies the algebra geometric condition that allows it to be considered a point in the quotient, namely polystability. So X is polystable. Yep. Oh, yeah, absolutely. Sorry. Yeah, that's a good point. So yeah, absolutely. So first of all, by some kind of continuity, you reduce to the case where you have a rational element that induces a C star action. Yep. So, and then you use this formula. Thanks. But otherwise, does not make much sense. Yeah, so the point is that the Lie algebra, not every element. I mean, if you imagine, I don't know, S1 squared, S1 times S1, then you'll have some elements that are rational, that kind of close up, their flows close up. And those things will give you C star actions, at least after some kind of clearing of denominators, while you'll have other elements of the Lie algebra that are irrational, so don't give you C star actions. But usually by continuity, you reduce to the case where you've got rationality. So you can associate C star actions. So rho from C star into G is the associated one parameter subgroup to V, where I reduce to V rational. I mean, said another way, actually, we're trying to define something that's actually linear in V. And so yeah, one can reduce to the rational case by that argument instead. Okay, so going back to the connection then between the algebra geometric quotient and the differential geometric quotient, the first result is that polystability, this algebra geometric condition, is equivalent to the existence of a G and G with our moment map mu of G of X being 0. So what does this say? This just says that G intersects mu inverse of 0, G dot X intersect mu inverse of 0 is non-empty. Namely, we can find a solution of this equation, mu of g of x is 0, if and only if the point is polystable. So that should be reminiscent of the Hitchin-Kobayashi correspondence. Second of all, we upgrade this to an isomorphism of the quotients. So mu inverse of 0, mod k. This is homeomorphic as a topological space to the quotient x mod GL. And I'll maybe just mention verbally a few other kind of relevant points. So one can actually directly produce the structure of a complex space on this thing. So these things can be singular, but nevertheless, you can put an analytic structure on the left-hand side in such a way that this becomes a biholomorphism as well. When you're taking a quotient in differential geometry, one of the selling points I mentioned that's come up in other talks is that we should be able to get analytic information about quotients from an analytic perspective. And so in particular, actually, this quotient, regardless of singularities, it always admits a natural choice of Kähler metric as well from this construction. So when we take the quotient differential geometrically, we get a differential geometric structure. Okay. Another comment that's going to be maybe slightly important is this all holds as well for x omega just compact Kähler, non-projective, where you just take a Kähler class that isn't integral, suitably interpreted. So one needs to interpret what GIT stability means. So this isn't a story that only lives in algebraic geometry. So I just want to say a word about the proof of this theorem because it'll come up. More likely tomorrow than today. So there are 3 proofs. Maybe there are more. If someone knows the 4th proof, I'd love to hear it. So 3 proofs. So the classical one is variational, i.e. you construct a functional whose critical points are zeros of the moment map. So you're trying to solve the equation 0 of moment map. And so what you do is you set up a variational approach by finding a functional whose critical points are that. You examine the properties of that functional, like convexity and behavior at infinity, and conclude that GIT stability is exactly the obstruction to finding a critical point. There is another proof that I think is less well known, where you use a continuity method. So you deform the moment map to one where you have a solution in some kind of continuous family, and you show again that the obstruction to deforming it to the original moment map is algebra geometric through GIT stability. So the original one is due to Kempfness, and it's the one that Kerwin uses in her thesis as well. The continuity method, sort of in a paragraph of a paper of Donaldson, one can elaborate upon it. Ask me over coffee if you'd like. And the one that I'll spend a little bit more time on is through geometric flows, or the gradient flow technique. Maybe this is more similar to what's in Kerwin's thesis. Okay, so proof sketch using flows. This is the briefest of sketches. So we consider a flow. We start off with our point x. We try to flow it in such a way that we get a 0 of the moment map. Okay, so we consider the flow. This is a principled flow. There's a way of deriving it just from the general setup. It's the gradient flow of the norm squared of the moment map after you choose an inner product. So you consider an inner product on K, the Lie algebra that's equivariant or invariant, sorry. So setting up a K equivariant isomorphism between the Lie algebra and its dual. Okay, the point then is that the moment map originally, it takes values in the dual of Lie algebra. Through this isomorphism, we can consider it as taking values in the Lie algebra itself. So in particular, we can consider, actually, I'll move. So we consider the flow starting from some initial point, x, and we move the point in the direction that's determined by the moment map as follows. So I want to give you a tangent vector to this point. And so mu of x, this now lives in K, which lives inside vectors, vector fields on x through this infinitesimal action, or at least we have an action, a map from one to the other. So x dot of t, so I view this as a tangent vector at the point x of t. So this is a tangent vector, but I use just my almost complex structure, essentially multiplication by I on this tangent space, and include a no minus sign here. Yeah, so I just move my direction, or my point, in the direction that the moment map is telling me to do. That's all we're doing. And yeah, from a more principled perspective, this is the flow that's decreasing the norm squared of the moment map. So zeros of the moment map are the lowest possible value of that. We're just trying to flow towards that. Okay, so the first main point is that this flow actually flows just in the orbit of x. So we can set x of t being g of t of x0, or of x, our original point, where g of t live in G. And we write our g of t in the following form. So we set g of t being x of minus I xc of t dot u of t. We're using reductivity here, where xc of t, these always live in the Lie algebra. So we can exponentiate elements of the Lie algebra, we'll get things in the Lie group. We multiply by I, or this is really corresponding to multiplication by j on this complex manifold, which is G. And u of t just lives in the compact subgroup. We don't really care as much about the behavior living in the compact side. We're more interested in the non-compact directions. Okay, so we flow inside an orbit. So we've just written down what we're flowing by, viewed from this orbit perspective. And so what we do is we show that the limit of these things, these actually converge. We're trying to extract a one-parameter subgroup, and we use these xc to construct a one-parameter subgroup in the limit. So we show that the limit, as t tends to infinity, of xc of t over t exists, say some xc infinity. These xc of t that we're getting from the flow, they're converging to something that is plausibly the sort of thing that we want to use to check the numerical condition for GIT stability. So it's this, and is rational. So one shows that it's actually rational. So induces rho in the same way that I mentioned before, which is a one-parameter subgroup of G. Then there's a dichotomy. So the limit as t tends to infinity, x of t, is some x infinity, which is a zeroth moment map, namely the flow converges within the orbit. Or we leave the orbit, in which case this rho is actually destabilizing. Or otherwise, if this situation doesn't happen, then mu of rho x is less than or equal to 0. So this one-parameter subgroup that we extracted from the flow is actually destabilizing. So, and if mu of rho x is equal to 0, then I just need to impose that this doesn't fix the point x. So rho does not live in the stabilizer of my point x. Okay, so this is a sketch partially because we're going to use this flow technique tomorrow as well. This is the end of the sketch of some of the ideas between the general connections between trying to solve equations like zero of moment map and algebra geometric stability. So if there are any questions on this, I'd be happy to take them. Okay, great. So now well, maybe let me just emphasize one more time. The philosophy behind this result says if we're trying to connect complex differential geometry and complex algebraic geometry, a good way of doing so is by trying to find equations that look like moment map equations. Because if we have a moment map equation, then we expect through this sort of philosophy that we have a connection with algebrogeometric stability. The motivating point that I mentioned at the start, that these questions are of interest because they're related to constructions of moduli spaces, is then precisely because the second part of this theorem, namely stability in algebraic geometry is related to the construction of moduli, and these moment maps are also related to the construction of quotients and hence moduli. And so we get this deep interplay between these various facets of geometry. Okay, so Z-critical metrics, connections. So there's this duality where we can either consider metrics or connections in the vector bundle geometry and moment maps. So my starting goal was to try to write down some general geometric PDEs for a Hermitian metric on a vector bundle. What we've learned now is that if we want that to have some connection to algebraic geometry, we should be able to phrase these PDEs through moment maps. And so what I'm going to do now is explain actually a very general and I think new way of constructing moment maps in complex geometry that will shed some light on this sort of question. So we produce general PDEs for Hermitian metrics on vector bundles and the point is to demonstrate them as moment map equations. That will then suggest connections with algebraic geometry into moduli theory. Okay. So I'm going to fix X, say alpha, where X is compact complex manifold, and alpha is just a Kähler class. So X compact, complex. And so because what I'm going to do first of all is really just cohomological. I'm just going to fix the class of a Kähler metric, so a Kähler class. So this is a 1-1 class on X that contains Kähler metrics. Okay. So what I'll write down is something that looks quite general, but what we're trying to do is give a recipe to produce general geometric PDEs. So we want some kind of general topological input that will determine a geometric PDE. So what I'm going to write down is the general topological input, and then I'm going to write down how to associate a PDE to that input. So central pairs, Z, which takes vector bundles, or more generally, coherent sheaves, to complex numbers. So what is this thing? It takes a vector bundle or coherent sheaf and gives you back a complex number, is a function of the following form. For those of you who have seen this sort of thing before, the form that I'll write down implies that this is additive in short exact sequences, which is the usual requirement that one imposes. But I'd like to be a little bit more explicit because we're trying to write down geometric PDEs, and so we want to write down something explicit. Okay, of the following form, so what should it take? It should take a vector bundle E, and we should get back a complex number. It's going to be defined through Chern classes. So we'll integrate over X some cohomological information. So we'll use the total Chern character of E. Oh, sorry, I was told that you can't actually read on the video the top part of this, so I'm just going to write a little bit lower. I see now that I've forgotten to do that for the entirety of this. previous part of the talk, but anyway. So Z of E. Okay, what is this? This is, again, integral over X. Total Chern character, so this is just the sum over J of the Jth Chern character of E that we defined through Chern-Bay theory, dot alpha, my Kähler class, to the L, and I'm going to invoke or involve another cohomological object, which is theta, and I'm going to sum over L. Okay, so what is theta and what do I mean by this? So for theta is just some other cohomology class that we fix. So it's an auxiliary information. So this is in H star of XC. So this is just in the direct sum over L greater than or equal to 0, HL of XC. Some complex cohomology classes. And this integration just means that, okay, so this is a class of various different degrees. But if I take the degree J piece, then, okay, I've got like a JJ class, an LL class, and what I do is I extract the n minus L minus J, n minus L minus J component. So this just means take the component that integrates to something non-zero, at least potentially, so the NN component here. Okay, so this is a choice that we make because we need to choose what theta is. Okay, but really this is just a topological choice. I'll give you an example of an interesting one that's kind of prominent in mirror symmetry in a moment. But really, you should imagine this is just a topological choice of some Chern characters and so on, which is additive in short exact sequences. In short exact sequences, which is the usual requirement that one that one sees in this story. Okay. Great. Okay, so to define a PDE, I'm gonna say, okay, so our variable is the Hermitian metric on the vector bundle, so the other things should be fixed. So I'm gonna fix omega and alpha Kähler. And I'm gonna fix a representative of capital theta through differential forms. So this is some cohomology class, so I just choose some closed representative. And I'm gonna assume that the 0, 0 component, as in the function component of theta, which must be constant just by compactness of x, this is just I. So it has to be a constant, and I can just scale everything. So this is I. So this is really a normalization. Again, not so fundamental. And so to this kind of input, what I want to do is define a geometric PDE. I'll actually do the most naive thing, which already works, which is to use Chern-Bay theory to define the PDE. Okay, so once I choose a Hermitian metric, so for any H, a Hermitian metric on E, we get curvature. So I'll normalize by scaling by I over 2 pi fh. And as I said yesterday, this is a 1-1 form with values in ND. Okay. So from Z, what do we get? So we just replace these classes by their Chern-Bay representatives. So we get Z tilde of EH. So this is going to be an NN form with values in ND, which I'm going to get by taking things of the form I over 2 pi FH, so that's the Chern-Bay representative that we obtained, to the J. So this, if we multiply by 1 over j factorial and take trace, this would be the representative of the jth Chern character. I can wedge by omega to the L, the same L up here. And then I can wedge with the corresponding component of theta. So this is just the n minus L minus j, or 2n minus L, 2L minus 2j component. So I'll just write it as n minus L minus j. So that's the component of theta that makes this an nn form. And I just sum over j, and I sum over L. Such that, well, I mean, I guess because this is n minus L minus j, this is always then an nn form. So this thing, where does this live? This is an nn form with values in nd. Okay, so we can make a definition. The definition, I mean, somehow one of the points of this story is that we're trying to do something that looks complex. Because from my original motivation, this theory of Bridgeland stability conditions, it involves a space of stability conditions that's a complex manifold. So our input, everything has to be complex. But at the end, when we want to PDE, we want to extract something real at the end. So what we need to do is take the imaginary part of something that we've constructed to be complex, and we'll get something real. Okay, so H is a Z critical metric. Okay, so I take my Z tilde of E H, so this is an NN form with values in ND. There's a scaling that I'll do that I'll tell you about in a moment. I just kind of rotate this complex valued function by a fixed angle. And I take the imaginary part, where I'll tell you what the imaginary part of an NN form with values in ND is in a moment, but really I just take the skew Hermitian part, and I ask if this vanishes. Okay, so again, the point of this whole complex formalism is to match up with this theory of Bridgeland stability conditions. From a pure PDE perspective, it's sort of an aesthetic choice rather than a truly consequential choice. Okay, so I need to explain two things. First of all, phi is the argument of Z of E, so it's the angle that we get, which I assume is so I assume Z of E is non-zero, so that's kind of basic requirement to make sense of this equation. That tells you what the inside interior of the brackets is, and I just need to tell you what imaginary means. And so this is an NN form with values in ND. I'm not going to touch the NN form component, really. And I'm going to say that imaginary means use the Hermitian metric to write this thing as a sum of skew Hermitian and Hermitian. If we did that for complex numbers, that would be imaginary real, and we just take the skew Hermitian component. So this denotes the skew Hermitian component. With respect to H. Okay, so because it's in the title of the talk, I'll say that we also say the associated Chern connection nabla is, instead of a Z critical metric, a Z critical connection. Okay. So what's the point? So I can view this on a fixed holomorphic vector bundle as an equation for a Hermitian metric, or I could fix a Hermitian metric and view this equation on the associated Chern connection in a given complex gauge group orbit. Yeah, so E is a holomorphic vector bundle. And so the only thing that's changing from this perspective is the Hermitian metric. But yeah, really just the point is that in the title of this thing, I used Z critical connections. And so I just want to say that there's this usual duality that you could consider this as an equation for a connection instead. But then you should work in just the orbit of connections that induce the same holomorphic structure if you wanted. Yeah. So that's not so important, but just to kind of connect. Any other questions? Yeah, so the point is that this topological input really comes from Bridgeland stability conditions. And the point is that for any such choice of input, we do get a geometric PD in a reasonably natural way. Except we would like to not just, one of the things I always found kind of amazing or frustrating in complex geometry is that it seemed like a lot of these geometric PDs that people were writing down came from magic somehow, or of the long-term history of Riemannian geometry or Kähler geometry. So we would like to derive these equations in a slightly more principled way, because if we want to do something very general, then it's important to give a kind of canonical recipe to derive things rather than something that looks a little bit more ad hoc. So the tools that I'm going to use are much more geometric. They really come from algebraic geometry and equivariant differential geometry. And so, yeah, they seem to be very general and very natural. Okay. So to demonstrate these equations as a moment map, we really use a geometric argument, but using equivariant differential geometry. So we use a geometric argument, something that really comes from kind of similar ideas in algebraic geometry, and tools from an old story in differential geometry, which is equivariant differential geometry. So in practice, probably I won't actually prove the moment map property today, but I will probably get to explain most of the tools that I needed. Yeah, equivariant differential geometry was developed by Cartan in the 1950s and saw a resurgence in popularity in the 1980s through work of Atiyah, Bott, and others. But then I think in the 90s and 2000s, corresponding tools from algebraic geometry became a bit more powerful, and these tools fell a little bit out of favor. But they seem very powerful, so it's a good chance also to advertise these interesting techniques. So equivariant differential geometry. So let K be some compact group acting on X, which I won't assume is compact. Actually, it doesn't really matter if X is even complex. So if you don't mind that, you don't have to assume it, but all of the X's in the stock will be complex, but not necessarily compact. That's important. Okay. So an equivariant differential form. Essentially, the philosophy of equivariant differential geometry is we want to do all of the things that we do in the basics of differential geometry, but incorporating this group action. So an equivariant differential form is a K-equivariant. It's an assignment of a sum of differential forms to every element of the Lie algebra of K, so to every vector field induced by the K action on X. So it's a K-equivariant, actually polynomial map, beta, which takes an element of the Lie algebra and gives us back a differential form on X, but possibly of varying degrees. So omega star, as usual, just means the direct sum over the differing degrees. K-equivariant, what does that mean? Well, we act by the adjoint action on the left and just by pullback on the right. What does polynomial mean? Well, this is a vector space, and so we can just consider polynomials in any basis, and it's independent of the choice of basis by some linear algebra. Okay, so what do we do in differential geometry when we have a differential form? We just, more or less, the first thing that we try to do is understand what the differential of a differential form is. So the equivariant differential of beta is the following. So what do we want? So dx of beta, to get a new equivariant differential form, what we want to do is take an element of the Lie algebra and get back more differential forms. And we can do that much like the moment map calculation in two ways. First of all, beta v is itself a sum of differential forms of varying degrees. And we can take the differential of that On the other hand, beta v, again, this is some differential forms, and we can take the interior contraction of that. So we sum these up. So when k is trivial, this is just the usual differential. This is kind of clear. And in particular, beta is equivariantly closed. If its equivariant differential is 0. So it won't really be important for this talk at all, but one shows using Cartan's magic formula that dx squared is 0, and that leads, therefore, to a cohomology theory, which is called equivariant cohomology. This is the Cartan, or differential form model for equivariant cohomology. Okay, so equivariant differential forms, they satisfy many of the same conditions that usual differential forms do. So equivariant differential forms, these are equivariantly closed. Differential forms are preserved by natural operations on equivariant differential forms, so by wedge products. And also fiber integrals, push forwards. So these are actually the only two properties that I'll use of equivariant differential geometry. So these are quite basic properties. So what I mean is beta wedge gamma, the wedge is just defined by wedging the form components. So the wedge product is defined in the natural way. And for equivariant proper submersions, the fiber integral is defined in the same way. So for x to be k equivariant, so I need a k action also on B. Proper, so the fibers are compact. That's what allows me, once I include the extra adjective of this being a submersion, so all the fibers are smooth, that allows me to take fiber integrals. So the fiber integral of x over b of beta on an element v of the Lie algebra, again, I just take the fiber integral of beta of v. This is just something that you define using that a submersion is locally a product, and you reduce to a single such product chart by a partition of unity argument. Okay, great. I'll make one more definition. That will probably be roughly it. Which is, we're trying to do vector bundle geometry. And so we would like some analog of equivariant differential geometry that incorporates vector bundles. I.e., what we want is some kind of equivariant differential geometry version of Chern-Weil theory. And the way that works is the following. So if k acts on E over x h, so what does my notation mean here? So k acts on x, it lifts to an action on E, so we fix a lift of an action, and k preserves this Hermitian metric h that we've chosen as well. So because we want to do Chern-Weil theory, now we should impose that E is holomorphic. And we get a moment map, what I'll call a moment map. I think this is slightly non-standard notation, but anyway. Okay, so how does a moment map work? So we take mu. Now it doesn't go from x to the Lie algebra, but rather we need to incorporate endomorphisms of E as well. So it gives us a section of Lie algebra dual tensor ND. So a moment map is a k equivariant map here that satisfies the usual moment map condition, but upgraded to sections of ND again. So if satisfying for all elements of the Lie algebra, we have an equality not of one forms with one, but one form's valued in ND instead. So rather than the differential, we have to take, let me write it like this. So for any B in K, we can consider the pairing of mu and v as a section of ND. But we can differentiate those sections using the natural connection that we have on ND. That gives us a one form with values in ND, but there's another way of getting a one form with values in ND, which is by taking the interior contraction of the curvature. So this is exactly how we did moment maps before, except now we've upgraded to sections of E instead, or sections of ND. So really we have a condition for a moment map that makes sense on the vector bundle. I'll just define the then corresponding equivariant Chern-Bay representatives, and I'll end for the day. So then tomorrow we'll be able to move to proving these equations or moment maps. So in fact, much like when we have a lift of the action to the line bundle, there's a canonical choice, which I'll just write down. It's a little bit more involved as a calculation than the case of a line bundle. So it's just the Lie derivative that we have because we have a lift of the action minus the connection. So that's a section of ND. So neither of those individually are sections of ND, but their sum is. Okay, and then the last thing is that we get equivariant Chern-Bay representatives, classes, or representatives, that's probably more accurate. How do we define this? So I'll write, again, I'll use a tilde. So they use the Hermitian metric on this holomorphic vector bundle, but I'll include ek. Okay, so this should be an equivariant differential form. So it should take an element of the Lie algebra and give me back some differential form. So what I'm going to do is consider FH, the curvature, plus the moment map paired with this element. So that's a two form with values in ND plus a section of ND, but that's okay. I scale this thing by I over 2 pi and j factorial. I scale it by I over 2 pi. I take the jth power. I scale by 1 over j factorial, and then I take the trace. Okay, and the point is that this is equivariantly closed. I'll just write in the corner, closed. Okay, so tomorrow we're going to use these just these basic properties of equivariant differential geometry and this theory of equivariant Chern-Bay theory in order to demonstrate that these equations are moment maps. I think actually the calculation from here will be pretty straightforward, but the point is that it's a very general technique that applies to every other context that I've tried in Kähler geometry. So it looks a bit more canonical than the previous constructions. And then finally tomorrow we're going to use these results to prove something like a Hitchin-Kobayashi correspondence for these equations, this large volume regime. Thanks, that's the end of the day.
So you said how the Kempf-Ness theorem is the philosophy behind this, the Hitchin-Kobayashi correspondences. Now, I would like you, if you can comment on the fact that that can go beyond philosophy, meaning that there is an infinite dimensional Kempf-Ness theorem. There have been some attempts to that, in particular, I know Ratu and collaborators. I was wondering if you can comment on those attempts of what is your view on that?
It's a very important research direction, but these are geometric PDs, and so they need some geometric PD theory to prove theorems. And so, I mean, the way that you prove the Hitchin-Kobayashi correspondence, which is Hermitian metrics on vector bundles, is quite different from the way that you prove the Yautian-Donaldson conjecture, which is about scalar curvature of Kähler metrics. In particular, I'm not saying the strategy is so different, or I mean, at least it can be made to be quite similar. But what I'm saying is the analytic details are completely different. So in both cases, you need some kind of completion of the space of metrics, but they work in a completely different way. I mean, they're really genuinely quite different parts of the technical part of the story. So it is true that, I mean, one can start ways of trying to prove these kind of correspondences using the ideas from any of the three proofs I mentioned in the Kempf-Ness theorem. But the analytic details are kind of distinct enough that it's sort of hard to write down a general philosophy as a theorem.
What I'm saying is whether if there is an infinite dimensional Kempf-Ness, once you are in the setup, you don't need to prove all these theorems. They are consequences. I mean, you don't need to prove the Hitchin-Kobayashi correspondence for Hermitian metrics or anything. These, once they are in the formalism, should be a consequence of this infinite dimensional version of the Kempf-Ness. You see, that is what is behind actually the attempt.
Sure. One can axiomatize the ingredients that go into it, but like, it's sort of not amazingly, I mean, it's sort of an interesting and important thing that people have been doing. Just, I mean, the analytic details are so different from case to case that it's not. So what I'll say is that from the variational point of view, you can really just write down, if you have these results, then you get a variational proof of some analog of this correspondence. Like people have done that. It's just a property of convex functionals on certain types of spaces. So that's completely viable. But then proving that those properties hold really involve case-by-case analysis that are like completely different in the vector bundle and the manifold case. I mean, one case where we will see that the the Kempf-Ness philosophy really does produce theorems is what I'll talk about tomorrow. That's not in kind of global problems, but deformation problems. What I'll prove tomorrow will really use the finite dimensional Kempf-Ness theorem. Yeah. It seems very important to do these things. Just, yeah.
So it seems like the theta is the important thing in your choice of your central charge.
Yeah.
Are there thetas that give you extra interesting things? Or?
Oh yeah, I forgot to write down an example. Sorry. Let me just very quickly write down an example, which is the deformed Hermitian-Yang-Mills equation. So it comes from a specific choice of Z that is especially interesting, I guess. That doesn't really involve a choice. So Z of E, deformed Hermitian-Yang-Mills, this is integral over x of I minus I alpha dot total Chern character of E. So that doesn't involve theta. That only satisfies the normalization that I chose if I put I to the n plus 1 here. So that is very important in mirror symmetry. So this is the central charge that produces the deformed Hermitian-Yang-Mills equation, which under mirror symmetry is mirrored to the special Lagrangian equation. So from what I'll do, you get a kind of non-mathematical physics derivation of that equation. That doesn't involve any extra class theta, but you can also include a B field by just taking an extra class beta. So beta is in H11 of XOR, no positivity assumed, but that means that alpha plus I beta, the mathematical physicists would call this a complexified Kähler class. And so if you want to include a B field in the story, which the mirror symmetry people do, then you need to include this form theta. Yeah. If you ask me why I should include a B field, then you should ask the mathematical physicists, I guess. But yeah. Yeah, so these are probably the two most important examples, clearly. Yeah. They produce completely explicit equations. So.
Any other questions?
The deformed Hermitian-Yang-Mills equation, I mean, it was introduced simultaneously by Lung, Yao, Zaslow, and these four mathematical physicists, Mariano, Moore, I forget one, and Strominger. Sorry for forgetting. Third. Yeah.
Well, if not, we'll break for coffee and come back at 10:50. Thank you again.